Thinking about specific heat capacity then. You know, if you take some coffee and you put it into a mug, two things will happen. The coffee will cool down, and I don't just mean because it's been sitting in the mug for a while, but as soon as you put it in the mug, the coffee will cool and the mug will heat. So what's happening is the mug is taking some of the thermal energy from the coffee, and they both end up at the same temperature. That's what everything's trying to do, to come to thermal equilibrium with its environment, so it ends up at the same temperature. So, coffee cools, the mug heats. Now, the mug has a certain heat capacity. That's the term we use to describe the energy required to change the temperature of an object by 1 degree C. So, if we had a mug with a smaller heat capacity, it would rise to the same temperature as the coffee by taking less thermal energy from the coffee, so both of them would end up at a higher temperature. But there are some problems with that, as we will see a little later. But this heat capacity is not terribly useful because it only applies to that mug. What we want to do, what we need to be able to do, is to choose the material to make the mug from to make the best mug. That's not just about heat capacity, of course, but it is one of those factors. So rather than talking about heat capacity of an object, it's more useful to talk about the specific heat capacity of a material. And the specific bit means 1 kilogram. So this is the energy required to change the temperature of 1 kilogram of the substance of a material. By 1 degree C, and just for completeness, without change of state. That'll become more apparent when we talk about latent heat, which goes on at a change of state. But that's your definition of specific heat capacity, the energy required to change the temperature of 1 kilogram of a material by 1 degree C. You can see the similarities, energy required to change the temperature of by 1 degree C. Well, you have an object here, you have 1 kilogram of material here. But this is the one we use. We might work out the heat capacity of an object, but we're starting from the specific heat capacity of the material it's made of. So, that's the definition of specific heat capacity. Units. Well, it is the energy required per kilogram per degree C. And the symbol we use for specific heat capacity is C. So let's then look at the equation for specific heat capacity. So our equation do this in symbols and we'll do it in words. The energy required is the mass of the material times the specific heat capacity of it times the change in temperature. Or the change in the energy is the mass times the specific heat capacity times the change in temperature. So there is the equation for specific heat capacity. So let's look then at an example. So here I have 500 centimeters cubed of water. Starts off at 20 degrees centigrade. Heated by a kettle to 100 degrees centigrade. I've told you the density of water is 1 gram per centimeter cubed, and the specific heat capacity of water is 4,200 joules per kilogram degrees C. How much energy is needed to do this? Well, we will start by writing down, or at least identifying what we know. We have 500 centimeters cubed, and each centimeter cubed has a mass of 1 gram. So that tells us we've got 0.5 kilograms, 500 grams. We have a change of temperature, starts at 20, ends up at 100. So those two tell us that our change in temperature is 80 degrees C. That's our mass. And here we have our C. So if we use our symbols, the energy is the mass times the specific heat capacity times the change in temperature. We have 0.5 times 4,200 times 80. And that is just 168,000 joules. Or 168 kilojoules. And just because you might get asked this sort of question as well, it gives you the time it takes and asks for the power of the kettle. Well, of course, you know your equation is power is energy divided by time, which is 168,000 divided by 140. And that gives you 1,200. Watts. So you have what specific heat capacity is, how it varies from heat capacity, and why it is more useful, the units of it, the symbol for it. And you have an example of how it might be used. Finally then, I just wanted to talk about conductors and insulators. So, your conductor will have a low specific heat capacity. If you think about it, that makes sense because conductors heat up and cool down easily. So it will heat quickly. It won't store a lot, relatively, because it hasn't taken very much energy to raise the temperature, so there isn't that much thermal energy stored. And it will cool quickly. Now, if you think those are properties that you really want in a saucepan, you might not have thought about it, but you want your saucepan to heat quickly. You don't want it to take very much heat to do it because you're paying for the energy. And you want it to cool quickly because once you're done with it, you want to be able to wash it, put it away. So your saucepan or a radiator in your house or in your car, you want it to get hot quickly. You want it to store very little energy. You don't want to have to put in loads and loads of energy in order that you get some heat out of it. And when you're done with it, you want it to cool quite quickly. These are properties of a conductor which they have because they have a low specific. Comparing that to insulators then, your insulator will have a high specific heat capacity, which means it will heat slowly. If you supply the same power to each of a conductor and an insulator of the same mass, the insulator will heat more slowly because it takes more energy to raise the temperature by 1 degree C. Therefore, at the same temperature, the insulator stores more energy than your conductor. And because it is an insulator, it cools more slowly. And one of the big examples of this would be the ocean. What you have here is a massive body of water, huge amount of water, absorbing enormous amounts of solar energy. But because it's water, it's an insulator, it has a high specific heat capacity, it heats slowly, but it stores a huge amount of energy. So when the seasons change and we go from summer into autumn into winter, all of this energy stored in the sea helps to keep the coastal areas of the land warmer than they would be otherwise. And because the sea cools slowly, that goes on for a long time. So coastal areas don't get so cold as inland areas.